Welcome to Cloud Native Live, where we dive into the code behind Cloud Native. I'm Annie Talvasto, and I'm a CNCF ambassador as well as a senior product marketing manager at Camunda, and I will be your host tonight. Very excited to have you everyone join today. So every week we bring a new set of presenters to showcase how they work with cloud native technologies. They will build things, and they will break things, and they will answer all of your questions. So join us every Wednesday to watch live. You can also watch on demand later if you miss an episode. So this week we have Andy Suderman from Warewinds to talk about building stability. But before we get to the topic of today, another exciting thing that's happening in the CNCF universe at the moment is the KubeCon Europe co-located event CFPs are closing soon. So if you have any talk ideas or you need to come up with ones, you can go ahead and submit them now. Soon will be too late. And as always, this is an official live stream of the CNCF, and as such, it is subject to the CNCF Code of Conduct. So please do not add anything to the chat or questions that would be in violation of that Code of Conduct. Basically, please be respectful of all of your fellow participants as well as presenters. So with that, I'll hand over to the speaker of today to kick off the presentation.
Great, thank you. Today I wanted to talk about resource requests and limits. And those who know me are familiar with some of the things that we do at Fairwinds. Resource requests and limits are kind of a pet peeve of mine, if you might say, or just a thing that I commonly harp on or talk about. And so I feel like we spend a lot of time telling people to set their resource requests and limits on all their workloads. And we tell them, different strategies for doing this and things like that. But what we don't talk about as much, at least out in the open, is what happens when you don't set them properly. Or what we don't get to see very often, except in real life clusters, are some of the negative side effects that can happen. And so I've been wanting to do this for a while. I put together some demos of kind of the different things that you can break. So hopefully today we'll get to break some stuff, see some things fall over, and have an idea of why that's happened.
Perfect.
So all the code I'll be using today, let's see, is the screen share up? Sorry, I can't actually tell. No. Can everybody see my screen here?
Now
there we go. Awesome. Thank you. All right. So everything I'll be doing today is in a GitHub repository that I made public this morning. So if you want to go tinker with this, what I have here is I have a GKE cluster. It's on 1.21. I have just N2 standard 2 nodes. So they've all got 2 CPUs and 8 gigs of memory. I've enabled node autoscaling across the 3 zones. So I, by default, have 3 nodes. I can scale up to 2 nodes per zone, giving me 6 nodes total. And then I have an application running in this cluster. So if you saw my last live stream a few months ago, I used the same app. It's kind of a fun little app. You can just go to the app and you can vote for where you want to have lunch. And the counter goes up. We see how many page views there have been. We see the name of the backend that we're connected to. And all of this is stored in a DB in the cluster. So if we go take a look at our cluster in the Yeld namespace, we have the app server, which is kind of the back end. We have the DB, we have the UI, and there's a Redis server for caching as well. And all the code to deploy this into the cluster is in this repository in the app directory. So if you want to deploy it to a cluster, you can just kubectl apply that app folder and get this app running. By default, it creates a load balancer. We have just an IP address here. Very simple setup, really easy to recreate. And right now, this app is, as far as we know, functioning. It seems to work. I can click. I can vote for stuff. And it seems to be doing its job. And we see it's using relatively low amounts of CPU and memory right now. So we have, one millicore and 36 megs of memory going on here. And so we have a happy app. That's great. So now the first thing I'm going to do is I'm going to show what happens when you deploy a noisy neighbor next to an application that's properly configured. So this app, if we look, we're going to focus on the app server today. So that's the back end for this application. It tends to have the most dramatic swings in resource utilization with traffic coming into the application, which is why we're going to focus on that. And if we take a look at that and we scroll down to the resources section, we see we have a resource request of 200 millicores and a limit of 200 millicores, a memory request of 100 megabytes or megabytes, and a limit of the same. And so what we have here is a guaranteed QoS class. And what this means is that Kubernetes and the kernel are going to try to their very best to give this all the resources that we have listed here. So what I'm going to do now is I have in here this core YAML. It works with an open source tool that we have. Essentially, I'm going to deploy a Helm chart. And I'm going to deploy a Helm chart, two different Helm charts that are going to spin up a program called Stress, which is just going to eat up CPU and memory in the cluster. And these two Helm charts that I'm about to deploy, these pods, are going to spin up, and they're basically just going to attempt to eat all the resources in the cluster.
Then there's an audience question. What tool is used to show pods, CPU/memory usage? Thank you to Moralitharn for the question.
Yeah, no problem. So I'm using here, this is K9's K9S. So it's just a kind of a TUI or a terminal user interface for interacting with Kubernetes. What we can do also, essentially what this is showing us is if I do kubectl top pods, I can see the current utilization of the pods in the namespace of my current context, which is the Yelp namespace. That's essentially the same thing I'm seeing here. The nice thing that K9S or K9s, I'm not sure how people say that, does for us is that it shows us the percentage of the request and the percentage of the limit that we're using as well. So that's percent CPU request, percent CPU limit, percent memory request, percent memory limit, which is kind of a nice thing to see as we go through the rest of this demo, which is why I'm using K9s in this case.
Great.
So I'm going to go ahead and install that Helm chart, and it's going to create the namespace called Stress, and it's going to deploy those pods that eat all of the CPU and memory in this cluster. And what we're going to see, because these pods are trying to eat up essentially as much memory and CPU as they can, but we're not requesting any CPU. We're not putting any requests or limits on these pods. What they're going to do is hopefully succeed at just overwhelming the node. And so we have a couple different ways to look at this. We can do kubectl top nodes, and we can see the CPU percentage and the memory percentage utilization currently. We can also see this in K9s by going to the node view in K9s. Or we have another tool that I typically use that we'll use a couple times throughout this demo. It's called kube capacity. And if we pass it the usage flag and make this a little bit wider because there's a lot of output, there we go. We can see the CPU requests and limit totals for the nodes. So what every pod on that node is requesting, the total limits of all of the pods on that node, and then the current utilization. And you'll notice that all three of these nodes are now pegged at 103% CPU usage and over 100% memory utilization as well. And hopefully our view down here will start to catch up with that. So, yep, there we go. CPUs at 2000. We have two CPUs on these, so that would be full utilization. It's 103% of the available CPU on the node. And so now what we're going to do is, well, first I'm just going to go click on the app and see if it's still working because that's like the easiest way to check. But another thing we have in place for this demo that's going to be useful is I have another file in the repo. It's a JavaScript file called load.js. And what this is going to do is I'm going to use a tool called K6, which is a load testing tool. And it's going to run a load test against this app. So essentially what it's going to do is it's going to go click on those buttons. So I'm going to go click on those buttons The default is set to 10 iterations. So it's going to go in, click on each button, and then, load the main page, click on each button, and it's going to do that 10 times. And then right now I'm using 2 what they call virtual users. So it's going to use 10 different essentially processes to do that. So they all kind of happen in parallel. And if we see here at the request duration, the average HTTP request duration for this test was 78 milliseconds, and the average iteration time was about 4.8 seconds. This is the baseline of what I expect for this app. So if I had run this before we started stressing the cluster, this is what we would have seen the app perform at. So we can see that the nodes being fully utilized and completely overwhelmed by this other application that is improperly behaving are not affected by are not affecting the application that we're running in our cluster, because we set our resource requests and limits to that guaranteed QoS class. This is why for anything that is critical or important to you, I generally recommend that you use that guaranteed QoS class. Set your requests and limits exactly the same, and set them to a reasonable number that you've tested.
Yeah, great. And I see a comment from Gary. Sorry, I showed up late. Not sure if I missed it. Was there a link given for any of these tools? I don't think we've given links so far, but we can see if we can add some during the duration of this webinar live.
Definitely.
Yeah,
If we can
perfect.
share the link to the GitHub repository, there's actually a section at the bottom that has a list of tools used and some links to those as well. So if we can just share that initial GitHub repository URL.
That has been shared. If it's the
Great.
GitHub Fairwinds resources demo.
That's the one. So if you go to that page and scroll to the bottom of the README, you should see most of these tools.
Perfect. So there you go, Gary. You can get the tools from there. And thank you so much for asking a question once again also.
Yeah, thank you. So now we've seen kind of well, actually, there's one more thing to show. Sorry. So the other thing we're going to do is we're going to go take a look at the pods in that stress namespace, because we're spinning up a whole bunch of pods that are attempting to use way more CPU and memory than it is available, and they have no resource requests and limits set on them whatsoever. And we're going to see something particularly ugly here. We're going to see a whole lot of pods that have been evicted because they're trying to use so many resources. And because they have essentially, the best effort QoS class, we haven't set any requests or limits. We've said just try to run this, see what happens. We're gonna see them get evicted as the node has the conditioned memory pressure. So we're running out of memory on the node. We need to find some pods to get rid of to make space for other things. These are the first on the chopping block to get removed because they have no resource requests and limits set. So now we've really seen the detriments of not setting any resource requests and limits. You're going to see, pod evictions. You're going to see potential issues with applications running, and then also the benefits of setting your resource requests and limits properly on your critical apps, so that they're not affected by other workloads in the cluster that may do bad things. Let's see. Any other questions about that? I think we're all right. So I'm going to delete the stress namespace, and we're going to stop stressing this cluster so much. We may have noticed here in our node list, we have 6 nodes now. So we've scaled up to our maximum number of nodes because of all of the extra pods I've been attempting to schedule and all of the memory pressure on these. It's also interesting to note that if we were using cluster autoscaler in this case, if this wasn't a GKE node pool, it's possible we would not have scaled up the cluster because there are no resource requests for those that needed to be scheduled. And so it may not have known it. The pods wouldn't have gone into a pending state, and the cluster autoscaler would have known what type of node to spin up. So in another type of cluster, this may have had even more detrimental effects, not allowing the cluster to scale up. All right. So So that's the first demo that's covered in the README, kind of describing what I did, what the different effects are. And we're going to go on to the second thing that can be a problem, which is not setting your CPU limits correctly. There's been a lot of debate in the community about CPU limits and CPU throttling and what you should set your CPU limits to, and Linux kernel bugs that resulted in increased CPU throttling more than you would expect. And so I'm just kind of cover what that looks like when you're experiencing a lot of CPU throttling. So the first thing I'm going to do is I'm just going to put a little bit of stress on the cluster. I'm just going to schedule some pods that use some extra CPU, just to kind of create a little bit of extra noise in the cluster while we do this. So this is the same app I was running before, but we're just stressing CPU, and we're not running nearly as many of the pods so that we don't get quite the same behavior. And then what we're going to do is I'm going to go take a look at the app server deployment, and I'm going to edit this, and we're going to find the resources block, and I'm going to turn this way down. So originally we had CPU requests 100, limits 200, or I think it should have been different than that, but that's all right. I'm going to turn this way down to CPU request of 10 millicores and a limit of 10 millicores. And we're going to take a look at the pods in that deployment. We're going to see what happens. So in the container creating state, and we're waiting and describe this, we're still pending. Grab this pod again. See if we see what's happening here. Pulling the image. Surprised this is taking so long.
Yeah, I think it's the demo effort that gets you every time.
Every time.
Yeah.
Live demos are a dangerous thing.
For sure.
All right, so we've started the container. It's running. We're waiting for it to go into a ready state. And now we start to see readiness probes failing. So we're trying to do a pull or a get request to the API endpoint get stats as our readiness probe in order to tell Kubernetes when our pod is ready to receive traffic. And these are just failing. And the liveness probe's now failing as well. It's the same API endpoint, so I would expect that. And if we try to get the logs for this pod, grab the previous, oh, there's no previous yet. We'll grab the logs from this pod. It's not logging anything. Nothing's happening. So essentially what's happening here is this: we have throttled the CPU down so far that this app can't even serve requests anymore. It just can't serve these requests. So if you have random intermittent failures of probes you can't explain, if you have a pod that doesn't come up just because the probes are failing and there's no logging, or maybe there's some logging, but it's very intermittent, this is usually evidence of CPU throttling. Now you can go look at graphs from Prometheus or from Stackdriver and construct graphs to see these, or whatever your monitoring tool is. But first thing I always look at when I see just unexpected probe failures, I know the app should respond on that endpoint, is the CPU limits, specifically the limits, because that's what controls the CPU throttling. So we're going to go back to our deployment, and we're going to edit this again. And I'm going to turn this up to something a little bit more reasonable. 10 millicores is tiny. We originally had 100 millicores. So let's bump this up to 40. Maybe we just started this thing up. Maybe we kind of expect it should only take, 40, 50 millicores. We want to be conservative. We don't want to give it too many resources up front because we want to have the most efficient cluster possible. And so we'll see if we can get our pods to even start with this new setup. If we look at the last one that tried to start, which is now terminating, we see it was well over its CPU limit and request, and it crashed twice, probably killed because of its failing probes. And so it just wasn't in a good state. So we're going to try this new one here, and we're going to see how it goes. So when you take a look at the logs on that, it's actually starting this time. So we have something good going on there. And it's running. Now we're just waiting for that readiness probe to succeed. And there it goes. So we're going to finish the rollout. I'm going to let it stabilize before we do anything else here. It is also fun to note that due to the wonderful features of Kubernetes, our app has actually been functional the entire time throughout this. That new pod, because of our deployment strategy, just didn't come up, but our other two pods were still running. And so if I had gone and clicked on the app or run my load test here, we would have seen that the app's still fully functional. All right, so we have one running, two running. We should only have two. So right now I have pinned the HPA to, oh no, I haven't. Hang on. Let me fix that. I'm not supposed to do that till later. All right.
And then we have a question from Mark about the Slack channel for the chat. I think it was linked or told a bit earlier. Yes, there we go. You can see there. So you can join in there, but obviously you can also ask the questions as you did, Mark, already via the chat in your preferred streaming provider. So that you already are doing really well on that front. Perfect. And then actually there's a question from Muhaffin again. Sorry if I'm failing in pronouncing the name, by the way. So they say looks like still CPU takes 100% off 40 M. Better to increase limit CPU 100 M. And then thank you so much to Jonathan for saying awesome. Great that you're excited to be here.
That's a great point about using 100% of 40 millicores as the limit. Right now we're sitting at 2% and 62% on our two pods that are running with, I would assume, very little to no traffic unless everyone watching the live stream has gone and started to click on this thing. And that is actually part of the demo. So I'm going to talk about that here in a second. So now we're sitting at 40 millicores. Our app seems to be running. We're passing the probes. Everything's kind of stabilized out. And so I'm going to run my little benchmark thing here that we ran earlier, that K6 load test. And I'm just going to take a look at the numbers here. Let's see what happens. And you may have already realized it's taking far longer than it did last time. And we see our average request duration was 500 milliseconds, and our average iteration was 12 seconds. So we've almost doubled the amount of time it takes to run this test. And this is a very small test. This is not indicative of any real life traffic or anything like that. If I ran this for a lot longer, turn up leave the views at 10, but change the iterations to like 10,000 and just let this sit, we will see that the app will use 100% of that CPU, and it's just sitting there and getting throttled over and over and over again. This would be another good opportunity to go take a look at our metrics graphs and see that throttling in action. You have to be a little bit careful with those kind of graphs because sometimes they can be misleading. Sometimes you see throttling and you're not sure if it's consistently a problem. What I prefer to do is take a look at actual latency. Just look at your application performance, look at those golden metrics, and see if your app is performing the way you expect. And in this case, at 40 millicores, we know that our request duration of 500 milliseconds is way too high. That's just not right for what we expect our application to do. And so the suggestion in the chat to bump up to a limit of 100 millicores, definitely a great idea. So we're going to do that. Let's find the resources block and bump this back up to 100 and 100, and hope our app starts to perform a little bit better. So it's also interesting to note that during that test, we never actually saw the CPU spike. So CPU throttling is a very complex mechanism. I've watched a few videos on it. I'm not sure I fully understand it, but I understand the effects of it. And so if we see that our app isn't performing and our limits are too low, we're seeing a lot of CPU throttling, turn those limits up, even if you're not necessarily seeing full utilization all the time. It's probably indicative of a problem with your resource requests and limits. So we're going to wait for this to stabilize again. Looks like we have 2 new running pods that happened a lot faster this time because we're not being CPU throttled quite so heavily. And let's run our test.
Yes. While we wait for that as well, there's another question from Antoine. Is it a good idea to profile applications to know worst case CPU usage and then adapt it?
I think that's a great idea to profile your applications. I think most people typically don't do that, or don't have the ability to do that, or just don't spend much time on that. But a great way to understand your application performance. You are correct in the last comment as well. The last comment is resource CPU is not necessarily, or I'm assuming you mean request. CPU request is not the same as limits. And that you can keep the request low and the limits high. And that is definitely true, but I am going to cover that a little bit later in the demos. And so we'll talk about that in a few minutes. So we reran our test. We're back down to 120 milliseconds, still a little higher than what we started with. I think we were at 200 on the baseline. So I'm going to go back and change this again, and we're going to go up to 200. Probably more than I actually need, but not a huge deal for this demo. We're just going to double it, see what's happening. And Antoine, you are very welcome. Thank you for asking questions. Keep the questions coming. It's a lot more fun when people are interacting. All right, so hopefully we've got this down back under 100 milliseconds. Let's see what happens. All right, yep, we're back down under 100 milliseconds. So 200 seems to be a pretty decent sweet spot for us. I'm going to leave it there for now, and we're going to move on. I believe the default in the actual YAML that we use to deploy this is 200 for both the request and the limit. It's set that way because we want to start with the best. So if you go to run this demo yourself or tweak this, you should start with that at 200. So that's the end of the CPU throttling demonstration. I'm going to move on to the third demo, much simpler than the last one. What happens if we just turn down the memory requests and limits? So we're going to edit this again. And this one, most folks are probably familiar with. This is a really common thing. It's relatively straightforward because the reaction to running out of memory is much easier to understand than than CPU throttling. CPU throttling, as I talked about, is fairly complicated. What happens when we turn the memory limit down is we're just going to keep getting killed over and over again. So if we go describe this, we see the last state was terminated. We are OOM killed or out of memory killed. The exit code for that is always 137. You may not necessarily see the reason as killed. You may just see terminated. But if that exit code is 137, you know there's not enough memory there, and your pod's just going to sit there and crash over and over again. So we're going to go back, and we're going to edit this again. Oops, wrong button. Edit. And find that resources, and we started at I think 50, so let's bump this up to 20, because obviously 10 megabytes was not enough for this app to even start. Just like in the CPU one, we weren't able to even get the app running on that. But let's bump it up to 20 and see if maybe it'll start on that. This is a little bit harder to do. Nope, it's not going to even start. I believe this app uses the most memory at startup, and so we're going to go back up to 40 here. Another great place to test this out in this app is the database. The database uses a lot more memory, but I'm trying to focus just on the app server today. All right, see if this new one can come up. 40 megabytes.
Yeah, there's another comment from Moraltrata. I feel so bad for the pronunciation today. So if Java-based app, minimum requirement 512 mil at least.
You are correct, but this is not a Java-based app. So, as far as I know, I actually don't remember exactly what it's written in. We can go find out. This is the repo. It's linked in my repo. And it looks like front end's JavaScript, back end is, I'm going to guess, Ruby by the GitHub analysis here. I'm not going to go dig through it because that's not important to the demo so much. So we're at 40 megabytes. We see just at steady state, I'm not running any traffic right now. We're using 70% of our memory limit. And so I'm going to run that load test again, and I'm just going to let it run for a few minutes here, and we're going to see a lot of times what we'll see is we'll see intermittent kills. So things won't necessarily, the app will start up, but under load, it will start to fall over. This is an opportunity to either adjust our memory limits up and have a little bit of buffer for it to surge, or it's an opportunity for us to turn on a horizontal pod autoscaler. And that's usually a much better option to scale horizontally rather than vertically. But we will see this app's not so much memory bound as it is CPU bound. It seems to use a fairly consistent amount of memory. And so I'm not going to likely get a ton of results out of this, but we'll see what happens. All right, so we're up to 85 and 83% on our two little pods here. And we go take a look. We'll see how much traffic. We're at 22,596 requests. We've done another couple thousand or so. The app is still running just fine. And we can take a look at the stats and look for duration, HTTP request duration. We're at an average of 67 milliseconds, so with a P95 of 102. So it's actually running quite well. Another thing to think about here is that 92% memory utilization might be a good thing. That might be exactly where we want to be. So if our golden metrics or our golden signals aren't showing any issues, if our latency is still where it needs to be, 92% is fine. I'm just going to let it run.
Great, and thank you so much for all the questions so far. And then there's another one from Antoine. Thank you. Is there a way to reduce the delay between the moment more resources are required and the moment a new node have been added to the cluster?
Reduce the delay between the moment more resources required. Predictive autoscaling. That would be the golden goose, wouldn't it? I don't know of any great things out there. There's a couple of solutions for sort of creating buffer space to reduce the amount of time it takes to scale up. It's the node over provisioner is a common solution where you essentially just run a very low priority pod that sits and holds those resources available and then automatically gets evicted when those resources are needed by something more important. And so essentially you keep those nodes kind of pre-warmed. So that can reduce the amount of time it takes to scale up. As far as predictive auto scaling, you really have to know like the patterns of your traffic coming in to be able to do that. And so it's a much more complex problem to solve. And I don't know personally of any great solutions out there for it. Generally, the solution is to just scale more aggressively. So turn your targets down or things like that. So we're still running at 93% here. We have an average request duration of 67 milliseconds, or 69 milliseconds. So we're actually doing quite well here, even at 91, 95% memory utilization. So I'm going to leave this. I think it's a great spot to be at. I don't really care that it's at 95, 96, 97%, as long as it's not occasionally getting OOM killed. If we do start to see those occasional OOM kills, then we may want to increase that just a little bit. But as I said before, I don't think this app's memory bound. It's very much CPU bound. And so I'm not going to worry about it. So that was the easy demo. Kills, very simple. We all relatively understand them. So I am going to move on to the fourth one. And this is my favorite because we see this a lot in the clusters that we run for our customers and that I've run for people in the past. It's very common to think, well, I know my app, I know my traffic's going to be bursty. I know that my resource utilization is going to be bursty. I don't need to request as much as my limits are. I'm going to take my requests and my limits. I'm going to use that burstable QoS class, and I'm going to set them really far apart. So I'm going to request 10 millicores because that's what I need to start with. That's really all it needs to get going. That's kind of what it uses at steady state. And I'm going to set my limits, and I'm doing this backwards on the screen because I'm trying to talk while I type. But I'm going to set my requests to 10 millicores, which we already know is far too little for this app from the earlier tests that we were showing on CPU throttling. But I'm going to set my limits of 500 millicores. So our limit is way up there. We're not going to get CPU throttling. I don't need to request as much. So it's a common thing, very common thing to do. And I'm going to do the same with my memory. This isn't actually in the script. I'm going a little bit off script here, but we're just going to see what happens when we do that. I'm going to set the memory request to 10 millicores and the limit to 100, which is way higher than what we had before. And so I'm going to set that. And at the same time, where this really becomes a problem, because it's not so much a problem when you're running a static number of pods. It can be a problem, but where this really, really becomes a problem is when we start using horizontal pod autoscaling. So I'm going to edit that HPA, that horizontal pod autoscaler, and I'm going to let it scale way up. So I'm going to say min replicas 2, max replicas 200. And what we're going to see here, if we take a look at that HPA, we'll see it's a CPU autoscaler, and we're targeting 50% CPU utilization. And the interesting thing about this is that horizontal pod autoscaler is based on request, and scheduling is also based on request. And so by requesting only 10 millicores, but allowing a limit of 200 or whatever I set it to, 500, that huge number, we're going to see some probably interesting behavior in our cluster. And this is where I like to go back to that cube capacity tool. So let's just keep watching this for just a minute. And actually, I'm going to keep running load against this. And I'm going to run a little bit more load. So say we got quite a surge in traffic. I'm going to use 30 virtual users instead of 10. Well, we're going to see what happens. So we're already sitting at 280% of our memory request and 278% of our memory requests on these two pods. So we're asking for not nearly enough. So we've scheduled this pod on a node thinking that it only needs 10 megabytes of memory and 10 millicores. The schedulers made this decision to put it somewhere, but that's way off because now we're using 3 times that amount already. So the scheduler's already made a bad choice because we told it to. And let's also, not demo one, sorry. We're still running some CPU stress in the cluster as well. So if we take a look at our HPA, we'll see that we are now 1,500% of our target CPU usage. And so what this is going to do is we're just going to explode the number of pods. We're just going to scale way up here for really no good reason. So if we look at our stats and take a look at our current request duration, let's see, nope. That's iteration duration. We're at 7 seconds, so we're a little bit high right now, but not massively. Remember, that was 5 earlier. If we look for the request duration, we'll see that we're at an average max of 900 milliseconds, an average of 200. So we're a little bit high, but we're not as high as we'd expect for the massive traffic spike that we had. So if we take a look at the number of pods here, we now have 75 pods. Take a look at our HPA. We're starting to settle down on our target here, but we probably don't need this many pods. For the amount of traffic I'm running, I would not expect to need 70 replicas. That's going to go up again in a second because of where we're at here. We're using 100 pods for a relatively small amount of traffic. So first, we're going to see problems with scaling. Scaling is going to happen too fast because our percentage of our request is so far off from what we're actually using. The second thing that we're going to start to see is nodes are going to start to get overwhelmed. So this is where that tool cube capacity comes back in that I talked about, written by an old coworker of mine, Rob Scott. And it's going to sum up your CPU limits per node. So if we look at all the pods running on this node, we add them up. You can get this information from a get nodes output, but this really sums it up nicely in an easy to read way. But you'll see that our CPU limit is currently, our summed CPU limits are currently 500, 400, 300% of our node capacity. So we have the opportunity to attempt to use 500% of our CPU, or I didn't really constrain on memory, but I've seen this happen with memory where you get to 300-400% of your memory available on the node. And as soon as you get a large amount of traffic and those pods start to consume more and more resources, your nodes are going to get overwhelmed. Things are going to start to fall over. We're going to start to see evictions like we did in that first test where we just spun up a whole bunch of stuff with no requests and limits. And it just really can result in a very unstable cluster. I'm not saying that all applications have to be guaranteed QoS class, but for your critical applications, use that guaranteed QoS class. And when you're going to use burstable, be mindful of the entire cluster and the ecosystem that you're deploying into, and understand that if your combined usage starts to get to a point where maybe you could hit 600% of a node, that's probably not a great situation to be in. And so be mindful of those summed limits and those summed requests. Let's see what's happening here. All right. So we'll just run the regular test real quick here and see what our current current numbers come back at. Looks like we're at 382 milliseconds average with an iteration of 10 seconds. So even with all these extra pods spun up, we're still not getting great performance. We are at 4 nodes. We haven't spun out any new ones. And we can take a look at the utilization output. Way too wide. Let's see. Our memory utilization looks good, but all of our nodes are spiked out on CPU, which is probably why we're seeing such high latency in our test, because with that level of utilization on the node, we're going to start to see more and more CPU throttling.
Great. And then there is an audience question again, which is amazing. So this is part of chaos engineering over Kubernetes from Jonathan.
I mean, you could kind of say that what I'm doing is a form of chaos engineering. If you really wanted to introduce some interesting chaos into your cluster, deploying something like that stress application to kind of attempt to eat resources would be a form of chaos engineering. So, sure, yes. Thanks for the question.
Good.
All right. Well, that's actually my last demo. I know we're a little bit early on time. Are there any other? I'm sure I can come up with some other ways to break this cluster. Any other questions from the Slack channel or anything like that?
Yes, perfect. There's a lot. Usually when we're near the end, the question amount just increases and increases, which is amazing to see, by the way. Thank you so much. So Dave asks, what do you prefer, K6 versus PyTest for endurance testing?
Sorry, I didn't quite catch that. Wait, what's the channel in the Cloud Native? I can go pull these up.
It was from Dave from YouTube side of things.
Oh, from YouTube. Okay. Oh, I see. K6 versus PyTest for endurance testing. I really enjoy K6. It's super easy to run. Writing the test is easy. Their documentation's great. Their cloud product's actually pretty nice. But it works for a whole bunch of different situations. I've been using it for a while. I don't know if I've used PyTest directly for this type of testing myself, so I don't know if I can necessarily give a good recommendation there, but huge fan of K6. It's very simple to get running.
Great. Keep the questions coming if there's more. We have time to take them. And then a LinkedIn user asked, is this Kubernetes native application?
No, I don't believe it is originally. I will say it runs quite well in Kubernetes. I've had good luck with it as a demo application. All the different pieces are nice. I grabbed the YAML for deploying it, modified it pretty heavily from the repository. So it definitely runs well in Kubernetes. Whether I could say it's necessarily like originally Kubernetes native, I'm honestly not sure.
Great. And thank you to you, Dave, by the way, first for asking the question. Great. So any other questions, or did you have some other way to break things more?
Oh, there's always fun ways to break things. So other scenarios we can get into with CPU and memory requests and limits. What's another common one that we see? I had an idea this morning and it just left me.
While we wait for that inspiration to strike again, I have a question actually. So you've talked a bit about different projects and so forth, but do you have a favorite CNCF project or another open source project regarding stability for Kubernetes that you can recommend?
Definitely. I'm a little bit biased in that we have some that Fairwinds has released some open source projects. Goldilocks is is designed for setting your resource requests and limits or setting a baseline for them using the vertical pod autoscaler project, which is part of the Kubernetes project, to get recommendations on how to set those things initially. So Goldilocks gives you a nice way to just view those on a single dashboard. And then as far as other stability issues that are not necessarily CPU limit and request based, we have a tool called Polaris that checks for best practices in your configuration of your workloads. So not just CPU requests and limits, but usage of HPAs and PDBs and other configuration things that are important, liveness probes, readiness probes, and stuff like that. So those are kind of our two main ones around stability. And then, of course, any of the tools that I showed today, all of the Kubernetes native tools, cluster autoscaler, metric servers, obviously in use here as part of GKE. So I think that's a good list of tools that I frequently use.
Great, perfect. And yes, Jonathan, thank you for hyping us up with great, awesome. Thanks for the share for this increased capacity over Kubernetes. Thanks a lot. Thank you for attending and thank you for asking questions. And good day and good night and so forth to you as well. And great. And then there's, I think, a question in the Slack side as well. So it's clear about setting good requests. What would be the best practice to set good limits?
Well, if you're gonna set your, I feel like I touched on this a little bit. So if you're gonna set your requests and limits different, if you're not going to use guaranteed QoS class, I would say a good guideline is to just not keep them too far apart. So I generally, like, as a very, very like total generic baseline, you could start with not setting it maybe more than 10% over your request, depending on various variables. Obviously, I can't give a blanket recommendation that's going to work for every workload in every cluster. There's just too many variables at play. So if you're going to use burstable, just don't keep them too far apart and be mindful of the whole ecosystem. But in general, if it's a critical workload, if it's your main application, if it's sensitive to being throttled or, any sort of disruption, then using that guaranteed QoS class is going to be your best route. So set your resource requests and limits the same and set them high enough that your app can function and you get the lowest latency possible. There's actually another tool out there that I forgot about that I've used in the past to do this. It's a much more complicated to use, but it's a really interesting concept. It was made by a company called Carbon Relay that is now part of Stormforge, I believe. Forgive me if I get your names wrong. But essentially what it does is it allows you to run a series of tests. So you set some variables that you want to monitor. You say, I want to look at my latency and I want to balance that against my, how many resources I'm using. So effectively my cost. And so I want to maximize, or I want to minimize latency. I want to minimize cost as well. And I want to tweak the CPU requests and limits. And so you give it a set of parameters, and what it will do is it will, and then you give it like a test to run, like a K6 load test or something like that. And it'll make the change, do the iteration of the test and measure those variables. And it'll do that over and over again and plug those into a machine learning algorithm and essentially give you a curve of like, okay, if you take your CPU request and do this with it, how does that affect your latency? It's a really interesting tool and a fantastic way to sort of get an idea of what's going on in the cluster around these types of things. So that could be a fun thing to look at for folks.
Great, thank you to Mosroy for that great question. And yeah, there's been a bit talk about the Slack as well. So there was a comment then, and if you send CNCF on YouTube your email for Monitoring, we will get you started on the Slack as well on that front. But yeah, those are the questions so far. So if there's any still, we do have a few minutes to take them. So keep them coming if there's anything that pops into everyone's head. Did inspiration strike, and did you remember the good way to break everything more? Or yeah.
It did not, actually. I was too busy answering questions. So I think these definitely cover the primary scenarios that we see most often. I'm sure there are dozens of other ways to break the cluster, but these definitely are the best, the most common ones that we see.
Yeah, and to Damjik and Briani, you can see the Slack channel on the stream itself, where the join our live chat on CNCF Slack there. And for the CNCF Slack, I think you can find that from the CNCF website, for example, a link to the Slack to begin with. It has also been linked to this chat, so you can maybe find it from there. But if not, I think CNCF website itself should have the link to the CNCF Slack, where you can then find the Cloud Native Live channel itself. And then there's a comment from Jerk saying, we've had long reviews on the request and lim range, and we've come down to 20% in our particular case.
That's great. Reviewing your CPU requests and limits is always a good idea, something you should definitely revisit on a regular basis. And definitely see, it's a balance between performance and efficiency, or performance and stability and cost, right? Because we can always get a very stable cluster by just turning our request and limits way up, always using, guaranteed QoS costs on everything all the time, and it will be very stable, and we won't have any rushes, but we're probably over provisioned considerably if we do this. And so reviewing that over time, looking at your metrics over time, and then making tweaks to those that don't affect your latency, or you have a reasonable range that you're shooting for with latency, is super important to do. So I think that's super great.
Great. Everything's going smoothly then over there. And then there's another question about what is this channel for the Slack, and it is still on the stream, so you can see it. You should see it like this direction. So join our live chat on CNCF Slack Cloud Native Live. So that is the Slack channel you should be joining. But obviously in here, we actually see comments from YouTube. So Stephen, we do see your comment here already live from there as well, or from LinkedIn or from the other places. But that is true. You can join the Slack as well and join the conversation on that side as well. And thank you so much for joining. And I've seen on the thanks and got it, and great messages on that side. And the Slack link, I think you can find that from the CNCF website itself, if I'm correct. And that should be there, so that you can join there. There we go. There's the link to the Cloud Native Slack once again.
All right.
That's great. Everyone's interested in continuing the discussion there. And it's the same channel that we have every week for these Cloud Native Lives. So if you hop in over there, you can then join in next week as well and see the chat in action in there as well as the links to all of the live shows are linked to that Slack channel as well. So that is a very nice tip for everyone here again. So we have 3 minutes left in our scheduled programming time. Do you have any final comments or recommendations, summaries, or anything?
Not anything new. Just make sure you set your resource requests and limits. I will continue harping on that probably for the rest of my career. Thank you so much to everybody for all of your questions and for listening. It's been great having you all here.
Perfect. Thank you so much for joining. So now that we have 2 minutes left, I think it's a great time to start wrapping it up. We've had a lot of great interaction. Thank you so much to everyone. So thank you everyone for joining the latest episode of Cloud Native Live. It was great to have Andy here talking about building stability. I and we both probably also really loved the interaction and questions from the audience. And as always, we bring you the latest of Cloud Native code every Wednesday. So you can join in next week and the next week after that as well. So next week we will have another great session from Jason Morgan talking about their amazing topics as well. So thanks again for joining us today, and see you next week.